Hey everyone, welcome to another episode in Physics is Fun. Today is going to be about solving a complex 2D kinematics problem. Let's jump into reading the question. A skier leaves a ramp of a ski jump with a velocity v equals 10 meters per second at the angle theta equals 15 degrees above the horizontal. The slope the skier lands on is inclined downward at phi equals 50 degrees and intersects the origin of the jump. Find A. The distance the skier jumps and lands at, and B. The skier's velocity components before landing. C. How might results differ if air resistance is in effect? We need a picture to help us with this one. We have a mountain and the slope, with a skier going off this ramp at this velocity at this angle above the horizontal. Velocity is 10 meters per second, and the angle theta is 15 degrees. Let's mark this slope triangle as well with this angle phi equals 50 degrees. This angle also intersects with the origin of the ski jump. And so with this in mind, our coordinate system can be the same. I know my picture is not lined up perfect. And this final distance of the slope is d. With a picture drawn, let's split the variables into x and y variables. Velocity initial x equals cosine theta times the velocity. Velocity initial y equals sine theta times the velocity. Velocity final x is unknown, and velocity final y is unknown. Both velocities we need to solve for. X initial equals 0, and y initial equals 0. X final is unknown, and y final is unknown. The acceleration of x is 0, and acceleration of y equals negative g. Let's write some more global variables like the theta equals 15 degrees and phi equals 50 degrees. The distance d is unknown, and the time initial is 0, and the time final is unknown. The velocity is 10 meters per second. At the ground of the slope, the x of the ground will be d times cosine of phi, and that gives us the x component. And so for the y of the ground, it will be negative d times sine of phi, as we are going down the y direction from the skier. To find when the skier lands, we need to find the value of d, and need to do a little prep to solve for d. To find d, we have the x and y components of the ground, and need to plug those into an equation so that we can set them equal to be able to find d. Time is the same for both the x and y directions, and usually the indication we need an equation with time when relating different components like x and y. Looking at the two equations with time, we do not have any velocity finals, and are left with the Fabro equation, x final equals x initial plus velocity initial x times time final minus time initial plus 1/2 times acceleration times time final minus time initial squared. Using this equation, let's solve for the x final and y final for ground. To solve for x final, x initial, time initial, and acceleration are all 0, so we can cross those out. This leaves x final equals to velocity initial x times time final. Let's replace the x final with our distance of x ground, so x final ground equals d times cosine phi equals our velocity initial x times time final. Let's also solve for time final here as well. Since we have two unknowns, we need to get rid of one, which will be the distance we're solving for, d. I rewrite these two equations so we can solve for y final now. For y, y final equals y initial plus velocity initial y times time final minus time initial plus 1/2 times acceleration times time final minus time initial squared. The velocity initial y and time final are both 0, so cross those out and get the y final to equal velocity initial times time final plus 1/2 times acceleration times time final squared. Replacing variables and y final with the y ground to get negative d times sine phi equals sine theta times velocity times time final plus 1/2 times negative g times time final squared. With what we have, we can use our time final equation to substitute into this equation and can finally isolate and solve for d. I rewrote the equations, and with our prep work done, we can find d, so it's time to calculate. Starting with the y final ground equation, negative d times sine phi equals sine theta times velocity times the time final, so let's plug in for the time final as d times cosine phi divided by cosine theta times velocity minus 1/2 times g times time final squared. So plugging in again, d times cosine phi divided by cosine theta times velocity all squared. The first thing to notice is our velocities happen to cancel out here. So we can just cross those guys out. And we also happen to have a sine theta multiplied by a term over a cosine term. So we can actually turn that sine theta over cosine theta into a tan theta. To solve for d, we need to isolate one term of d. So I rearranged all the d terms out in front to get negative d times sine phi equals d times tan theta times cosine phi minus 1/2 times g times d squared times cosine phi squared divided by cosine theta squared times velocity squared. And with all the d's in front, each term contains one d, the third term having a power of 2, so I cross out one power d from all three terms to get negative sine phi equals tan theta times cosine phi minus 1/2 times g times d times cosine phi squared divided by cosine theta squared times velocity squared. With one d left, let's isolate it by adding sine phi to both sides and adding 1/2 times g times d times cosine phi squared divided by cosine theta squared times velocity squared to both sides. Cancel the sine phi on the left and that big one on the right. This leaves us with d times g times cosine phi squared divided by 2 times cosine theta squared times velocity squared equals tan theta times cosine phi plus sine phi. To finally solve for d, let's multiply both sides now by the reciprocal, 2 times cosine theta squared times velocity squared divided by g times cosine phi squared. Distributing and multiplying, canceling the g, cosine phi squared, 2 cosine theta squared, and velocity squared, leaving with just d on the left hand side. D finally equals 2 times cosine theta squared times velocity squared divided by g times cosine phi squared times tan theta times cosine phi plus sine phi. Now we can plug in to find the value for d. So d equals 2 times cosine of 15 squared times 10 meters per second squared divided by 9.8 meters per second squared times cosine of 50 squared all times 10, 15 times cosine 50 plus sine 50. Calculating this all out, we get d to finally equal 43.24 meters. With that part A is solved, write in d equals 43.24 meters, and moving on to part B, asking for the final velocity components. Time final and the velocity finals are unknown, so to find the final components, we should find the time final using our time final equation we wrote, and can finally solve for the other components with the time final. So time final equals d times cosine phi divided by cosine times theta times velocity, plugging in to get 43.24 meters times cosine of 50 divided by cosine of 15 times 10 meters per second. Cancel the meters and bring the seconds up to get our final answer of 2.87746 seconds. Write that in the time final now, leaving just the velocity x and y components to find. So it's time to calculate. For the velocity final x, we have a written equation of velocity final x equals velocity initial x. So plugging in a velocity final x equals cosine theta times velocity, which equals cosine of 15 times 10 meters per second, and get 9.8 meters per second as the velocity final x. To find y now, we can use the velocity final y equals velocity initial y plus acceleration times time final minus time initial. Time initial is 0, so cross that out and plug in to get sine theta times velocity plus negative g times time final. And finally calculating velocity final y equals sine of 15 times 10 meters per second minus 9.8 meters per second squared times 2.877 seconds. Simplifying to 2.588 meters per second minus 28.19 meters per second, getting a velocity final y equals negative 25.6 meters per second. Part B is solved. Let's write those values in now and discuss C. C. How might results differ if air resistance is in effect? Thinking about how air affects things like paper and planes, it can apply a pseudo lift force, slowing down the object's fall. If the skier is jumping and creating air resistance, they will fall much slower and thus have more hang time in the air, clearing a longer travel distance. Calculating without air resistance is a smaller number than what is achievable as a ski jumper. There was quite a lot of work in this problem, but found the way to relate our given velocity to the unknown d, finding d equals 43.24 meters, allowing us to find the air time of 2.877 seconds, giving the final velocity of velocity final x equals 9.659 meters per second, and velocity final y equals negative 25.602 meters per second. I hope these intro problems are as helpful for you as they are for me. Thanks so much for watching. Hope you come back to learn more exciting material, and see you next time.